Hello everybody, welcome to this new week on the course of Responsible AI. So in this week we will start looking at a new aspect of AI, which is in terms of making AI responsible, and the aspect that we will cover in this week is privacy in AI/ML. Why does privacy fall in the bigger scheme of responsible AI? Because let's say you have an AI or ML algorithm which takes in a lot of data and does some processing and then outputs a model from this algorithm. And as users who are providing data for this algorithm, one must be very clear whether by providing data to the algorithm and the algorithm outputting a model. Nothing about the data itself is revealed to a third party via the model. To make this more clear, let's say you have some data and the data goes into an algorithm, and let's call this an ML/AI algorithm, and out comes a model, and this model is given to the world, right? So the world, let's say, has access to this model. Now, let's say, to give you an example, maybe the data that we have are healthcare records, and the algorithm is a simple binary classification algorithm which takes all these healthcare records and trains a model which predicts whether a given person has a certain disease or not, right? So the model, let's say, is your standard neural network or a support vector machine or any of your favorite algorithm, binary classification algorithm, which predicts disease equals yes or no. Let's say that's what the model does, right? So now, for example, the disease that we are dealing with might have some social taboo attached with it, right? So as a user, right, so as a, or rather as a data provider, I may not be very happy if the world looks at this model, which is just a mapping from features to labels, and somehow is able to figure out whether I have a disease or not, right? So that's the information that I want to be private, right? So we want the data to be private, right? So we want to be private. For whatever reasons, in the healthcare case, this might be disease information. Maybe it's a financial records data, where in case your salary might be something that you want to protect or make it private, whatever it is, right? So we are going to assume that the data has to be private, and now by running an ML or an AI model on the data and giving the world, the model, access to the model, an adversary in the world who has access to this model should not really be able to reverse engineer my data. If that reverse engineering is possible, then I as an user will not be very confident in giving my data to the model, right? So to the algorithm to generate a model. So now, how can we protect, right, so our data in this process, right? So this is the bigger question that we will ask. And the first thing that might come to our mind is the following, right? So I have a data, and then there is an algorithm, and the model is revealed to the world. Well, can we not use standard cryptographic techniques to encrypt the model? And then when you want to do an inference using the model, let's say, when I say inference, when you have a test data point, you want to figure out whether this test data point has the disease or not. Maybe can we do everything in an encrypted fashion, right? So one of the first solutions that one might think about here is a cryptographic solution, right? So what do I mean by that? I mean that the model is in some sense encrypted and given to the world, and if the world wants to use the model, well, the world does not have access to the model, but then it only has access to the functionality of the model, but then because everything is done in an encrypted space. There are two reasons why we may not want to do this, or we may not be able to do this. One is because it is unclear immediately whether you can always do this inference in an encrypted space, right. So, it is not necessary always that given this feature, there is some function that maps this feature to a label. In this case, the feature could be your healthcare information, and the label is whether the disease is present or not. So, this mapping is essentially a function, right. So, and then what we are saying is that we want to be able to evaluate this function without revealing the function itself. That is, if we want to be able to perform the process of evaluating the function in an encrypted space, and that may or may not be possible depending on how complicated this function is. So, that is one reason why this is not necessarily always the preferred solution. The second reason is that it might be an expensive solution, right. So, to do encryption, decryption might take a lot of time, etc., and we typically try to avoid cryptographic solutions to this problem. Now, how else can we do this? Well, the solution that we want to look at least in this course, is not this cryptographic solution. It's not that it's a bad solution. It's just that that's not the focus of this course that we are trying to talk about here. Instead, what we are going to look at is a statistical solution to this problem. So, essentially what we are going to try to achieve is a statistical solution to privacy. So, we'll talk about what a statistical solution to privacy means as we go along, but so that's the bigger idea is that somehow we want to use statistics, which means that somehow we want to incorporate randomness into the bigger picture and somehow use randomness in an intelligent fashion so that we can achieve privacy. So, that's the overall goal of what we are trying to do here. But before we proceed further, let me also tell you that some of the techniques which also might seem obvious, or first cut solutions which may not necessarily work. One of the solutions that one might think about is, let's say we are in a simpler situation where we want to we want somebody to develop a model for us, and then we want to give them the data, which is a slightly different setup than what I have said here, where the data is given to a algorithm, and the algorithm outputs a model. Instead, let's say I want to give you the data, and then you want to develop a model based on that. Now, if I want to protect my personal information, one of the things that might come to mind is, can I not remove all personal information, right? So, in other words, can I not just anonymization, right? So, I'll remove all the name, all any other information that might reveal anything about me, might identify me specifically, my name, my address, my PIN code, etc. These are the things that maybe I'll remove from my database, and then I'll give you only the remaining data. And now, if I run a model using this remaining data, one might be tempted to think that, well, that should be private because it's not using any of the identifying information. So, this was considered to be something that would work for a long time, but there have been several instances where people have demonstrated that anonymization is not really a proper solution. And one of the famous examples of this is the case of the Netflix data set, where Netflix put out this challenge, used to put out this challenge where they would give you information in the form of user cross movie ratings. So, basically Netflix data set would look something like this. You have, let's say, a big matrix, there are a bunch of users, let's say n users, and then there are a bunch of movies, m movies, and each user rates a bunch of movies, right. So, the movies that he or she has watched, that user would rate that. Maybe this user says 5-star for a particular movie, 3-star for a particular movie, and so on. And then there are going to be a lot of movies that the user does not rate, right. So, because the user clearly has not every user has watched every movies. So, this is a very sparse matrix. Now, the goal of the challenge itself was to somehow use this matrix and complete this matrix, right. So, meaning that if I give you a specific user and ask whether, what would be the rating of this user for a particular movie if this user had watched that movie, right. So, which means that the entry in the matrix is not given to you, but can we use some kind of information correlation among users in terms of how they watch movies, etc., and then can we fill the missing entries of this matrix, right. So, which means that you will be able to answer questions like, what would be the possible rating a user would give for any specific movie, right. So, that was the Netflix challenge to kind of complete this matrix. And of course, Netflix, when they released this data set, this was back in the early 2000s, when they released this data set, they made sure that the data set was anonymized, right. So, they did not reveal any user information because, well, one can argue that the user's information about the movies is a sensitive information, whether the person watched a particular movie or not, and so they did anonymize this information. But what happened was, there were some successful efforts at de-anonymizing certain user information from this database. And the way they did it is, when I say de-anonymization, I mean that you were able to figure out who at least partially, some of the users who had watched certain movies, you were able to figure out who these users were. Of course, Netflix had anonymized the data set here for this particular for this particular matrix that they revealed to the world, but the attack, so to say, the de-anonymization attack in this case kind of used auxiliary databases. For instance, in this particular case, they used information from IMDb, which is a movie server, which also has a lot of information about people watching movies, giving reviews, etc., etc. So, they used these auxiliary databases and somehow tried to correlate these two databases and figured out information about which user in the Netflix database watched which movies, right. So, the user's identity, which Netflix tried to protect, was in fact compromised because this information was available in a different fashion in a different database which was publicly available in the internet. So, anonymization not necessarily always works because there might be side information, side attacks, side information attacks, and so we cannot just rely on anonymization as a tool to achieve privacy. And that's why in this course, what we will see is a very robust and very interesting notion of privacy, which is neither cryptographic nor based on these heuristic techniques like anonymization, but as a more well-founded technique which is statistical in nature. Okay, so to understand this, we will begin by looking at a very simple example, and then slowly build our intuition as to what the notion of privacy that we care about, and we will eventually end up in the machine learning context, right. So, we, instead of directly jumping into the machine learning context, what I would like to do is start with a very basic example, a very simple example, and then slowly build it from there, right. So, we will start with a very basic example now. Okay. So, the example that we are going to consider is very super simple. So, let us say we have n people, let us say n individuals who have participated in the electoral voting process of the country in a particular year, let us say, right. So, maybe this n is 100, we are looking at a survey of 100 people, let us say, right. So, now the information that we care about, which I am going to call as data, is a very simple piece of information. It is just the following. So, it is x1 dot 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 xn, where xi is just 0 or 1. If it is 0, that person did not vote. If it is 1, that person voted. Let us say this is the information, right. So, and now I am a surveyor, so I am just asking 100 people at random, and I am asking them, did you vote in the previous Lok Sabha election, let us say, right. So, and the truth, right. So, this is the truth, which is which I'm going to call as x1 through xn, which means that if x50 is 1, then that means that the 50th person voted. The truth is that the 50th person voted. Now, for whatever reason, I am interested finally in, after I get this information, I am interested in knowing that what is the fraction of people who typically vote in this country, right? So let's say that's my goal of my experiment. So that's where I will eventually, right? So I collect this information from 100 people, I'll do an average, and that average is a kind of indicative, at least I would hope, if everybody is truthful, is indicative of what is the fraction of people who typically vote in an election, let's say in a locality or something like that, right? So that's the setup. Now, for whatever reason, let's say people are not very happy revealing truthfully or revealing their information, right? So maybe there is some again a social taboo attached. Somebody did not vote, and they don't want you to know that they did not vote, right? So because that means that they have not done their duty towards the country, and they don't want to, um, you to know that, let's say, right? So now one thing that they can do is the following, right? So they can lie basically, right? So which means that what they could do is, they may not provide you any information at all, and one way to do that would be to, I come and ask you whether did you vote or not, and you might just, pick a coin from your pocket, flip it. If the coin falls heads, you would say you voted, otherwise you will say you did not vote, right? So it has no relationship whatsoever to the actual truth of whether you voted or not. It's just a random 50-50 chance for your response being yes or no, 0 or 1, voted or not voted. Now, if all the n people did that, what I am essentially seeing as the person who is doing the survey is n coin toss answers, where each coin toss is just a flip with 50% chance of heads and 50% chance of tails. And that's not really going to help me at all, right? So because I really want to know what is the truth here, right? So what is the average number of people of these 100 people who really voted? But if everybody is just giving me random answers, I can't really learn anything. But that is the most private answer that somebody can give, right? So because everybody is just tossing coins and giving me the answer, and from that answer that I am seeing, I will never be able to say whether somebody voted or not, even at an individual level, right? So there is no information that I am getting from this coin toss about the truth itself, right? So it's a very private way to reveal information, that we agree, because there is nothing about the truth that gets revealed from this information that I am providing to the person who surveys. On the other hand, it's a useless information from a surveyor's point of view, because all the surveyor is getting is just a random n bits of randomness, right? So there is nothing that the surveyor is going to gain information about the truth. So that's one extreme, where you are very private, but then the utility of the information that you are providing is simply useless, right? So it's not useful at all. On the other extreme, I can actually be truthful and reveal x1 through xn itself, right? So everybody is truthful and they are revealing their true voting, did they vote or not. Now, that's the most useful information, right? So because I get an exact value, which is the average of x1 through xn, but it's not private at all, because I know whether each person voted or not. So on the one extreme, you have privacy, right? So this is privacy is 100%, utility is not there, where randomly toss coins. That's one extreme. On the other extreme, reveal the truth. Well, that's not at all private, but utility wise, you have all the utility, right? So you kind of exactly get what you really want to get. Now, neither of these is useful, because from this is the randomly tossing coin is useless from the surveyor's point of view. The revealing the truth is useless from the data provider point of view. Now we somehow want to be somewhere in between, and that is going to be our first simple algorithm, which is what is called as randomized response. It's not too hard to guess what this algorithm would be from our discussion so far, right? So because you somehow want to be in between these two extremes, so you do want to randomize, but you don't want to reveal too much information also. So that's going to be a tricky balance, but somehow we are already seeing what this algorithm is going to be. And in fact, I mean, I would encourage you to pause and think, what would be your algorithm at this point? How would you randomly give an answer? And we'll see what is one way to do this in a minute. Okay, so let me tell you what might be one way to do randomized response. As I said earlier, the truth is x1 to xn, where each xi is 0, 1, and then, but I am not going to reveal the truth. What I will reveal is the following. I'll reveal the ith person will reveal yi, right? So instead of xi, the ith person is going to reveal yi, and yi is going to be xi, which is the truth, and that is going to happen with probability. And I'll put this down and explain what this probability intuitively means. So with probability, e to the epsilon by 1 plus e to the epsilon, and the ith person would say 1 minus xi. 1 minus xi is just, if xi is 0, 1 minus xi is 1, and if xi is 1, 1 minus xi is 0. It's basically flipping the answer. With probability, well, the remaining probability, which is 1 by 1 plus e to the epsilon. Right. So in other words, what this means is that I am revealing the truth with this probability, and I am not revealing the truth. This is falsehood, right? So it is not the truth with the remaining probability. Now, one might wonder, why is this strange form e to the epsilon by 1 plus e to the epsilon? That's just to make sure that epsilon is a parameter that we can play around with, and e to the epsilon is going to be some number which is going to be greater than 1, and so what would happen is e to the epsilon divided by 1 plus e to the epsilon is going to be something that is going to be greater than 50%, right? So basically we want to reveal the truth with more than 50% chance. If epsilon is 0, if I set epsilon as 0, then this value e to the epsilon is 1, so this is going to be 1 by 1 plus 1, which is half, right? So which is our previous case where I'm just randomly tossing a coin. But as epsilon becomes more than that, right? So if epsilon is greater than 0, so then what would happen is, I want this value to be, this value will be greater than 0.5. So I am revealing the truth with more than 50% chance, right? And I am saying the wrong answer with less than 50% chance. Of course, epsilon is a tunable parameter, and to make sure that everything is positive, and in the way that they sum to 1, etc. So that is the reason why it is of this form, right? So nothing more than that. So now the question is, how do I choose this epsilon, and what can we say about this randomized response mechanism, right? So what guarantee do we have about this simple technique itself, is what we are going to see next. Okay, so to understand what are some good properties of this randomized response mechanism, let's consider two data sets, right? So consider two data sets, and I'll talk about why we want to consider two data sets in a minute. But let's say we have a data set X which has these x1 through xn, and we have an x prime, which is another data set, and it can be x1 prime to xn prime. These are two different data sets, but for the moment let us assume that these two data sets are not completely different. These two data sets are almost the same, right. So, we are going to assume that xi equals xi prime for all I in 1 to n minus 1. In other words, you have 100 people in both the data sets, but 99 of them are the same in both the data sets. There is just one person who is different in data set 1 and it is a different person in data set 2, right. So, which is the 100th person in this case. It need not be the 100th person, it can be any person, but for simplicity we will just consider it as 100%. I mean, it is without loss of generality, as we will see. Okay, so let us say we have these two situations, right. So, in one situation it is x, it's the data set x to which we are doing the survey. In another situation it's the data set x prime to which we are doing the survey, right. So, and the point is x and x prime are almost the same, that is just one person who is differing from x and x prime. So, now what gets revealed, right. So, this is the truth, but what is really revealed if it had been x, right. So, if I had done the randomized response mechanism on x, which means that there is a fixed epsilon. When I say randomized response mechanism on the data set x, everybody in that data set x is going to toss a coin with probability e to the epsilon by 1 plus e to the epsilon of falling heads. If the coin falls heads, they will report their information truthfully, otherwise they will flip and report. That is what I mean when I say RR of x, randomized response of x. It means that everybody in the data set x is performing this randomized response mechanism and then giving me the answer, right. So, let us say RR of x is y and y is just y1 dot 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 yn. Okay. So, I in fact see y1 to yn. Remember, yi is also 0, either 0 or 1, but then the relation to x depends upon this coin toss, right. So, that internally happens. Now, RR of x prime similarly will be y prime, right. So, if I had done the survey not on x, but then on x prime, I would have gotten y prime, which is y1 prime dot 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 yn prime. Y prime is also 0 or 1. So, there are two situations. I mean, I do the survey on x or I do the survey on y. Now, I want to ask, well, I don't know the truth, right. So, I mean, because there has been a mechanism that has altered the truth and I am only observing some altered version of the truth. Now, which means that essentially I am observing a bit pattern. There are n people, so I am observing a bit pattern. Now, I am trying to ask the question, if I see a bit pattern, I ask a reverse question, did this come from x or did this come from x prime? Let us say that is the question I am interested in, and we will see why this is an interesting question to ask in a minute, right. So, I have done the survey and I have gotten the response, right. So, and now I tell you the response. You see the bit pattern, right. So, B1, let us call the bit pattern as B1, B2 till Bn, right. Now, you ask the question, did the randomized response on x generate this bit pattern or the randomized response on y generate this bit pattern? Now, what we want to try to see is, can we tell them apart? That is the bigger question we will ask, but let us get to that slowly, right. So, now, which means that, remember, this bit pattern is a random pattern. Why is it random? Because the process itself has tossed coin and then revealed some information. So, this is a random process. So, I want to now ask the question, what is the probability that the randomized response on x generates a particular bit pattern B, right. So, when I say bit pattern, it is to be understood, I am thinking of it as B1, B2 till Bn. Example, if I ask 5 people and now maybe this is some bit pattern 0, 1, 0, 1, 1. It can be any bit pattern, right. So, let me fix a bit pattern. In this case, the bit pattern 0, 1, 0, 1, 1, right. So, I observed 0, 1, 0, 1, 1 and I am asking what is the chance that a specific x data set, after going through the randomized response procedure, generated 0 1 0 1 1. What is the chance of that happening is the question that I am asking. Well, what is that chance, right? So, this just means that this is just the probability that y1 y2 dot dot yn, which is the randomized response output of from x, right. So, that is what I have written here. So, y1 y2 yn equals b1 b2 bn. This is just this chance, right. So, if it had been from x, then I would have gotten y1 to yn, and I am asking what is the chance that y1 to yn equals b1 to bn, but every person is independently tossing the same coin and then flipping it or not flipping it. So, which means that this chance, it is like I am collecting n different data points and all of these are independent and identical. So, this can be written as product of I equals 1 to I, the probability that yi equals bi, which is same as the product of I equals 1 to n 1 to n minus 1 probability that yi equals bi into probability that yn equals bn. I am just writing the nth guy separately out because by our assumption the nth guy is the one who is different from the data sets x and x prime. Okay. So, let us call this one, and just to be sure that this happens because independence of y1 to yn. Right. So, every person is doing this procedure independently of flipping coins, and so the joint probability is a product of their probabilities. Okay. So, this is the chance that I observe a bit pattern B, and then what is the chance that the randomized response acted on the data set X to produce this bit pattern. Now, I can ask the same question about the data set X dash or X prime, right. So, I can ask what is the probability that the randomized response on X prime generated the same bit pattern B, right. So, that we know, I mean, by our previous discussion. Now, it's just product of I equals 1 to n probability that yi prime equals bi, which is I know is just the product of I equals 1 to n minus 1 probability that yi prime equals bi into probability that yn prime equals bn. Again, by independence, it is the same thing, right. So, if x prime had generated the bit pattern B, then this is the probability of that happening. But we know x and x prime are almost similar, which means that this part is exactly the same for both, right. So, which means that I can write this as product of I equals 1 to n, in fact probability of yi equals pi into probability of yn prime equals bn. This I can do. Right, yeah. So, what does this tell me? Well, this is telling me the following. This is, let me call this 2. Yeah. So, this is then telling me that okay. So, now I can ask the question. I need one more small calculation. So, let's look at the following calculation. So, what is the probability of yn by equals bn divided by probability of yn prime equals bn, right. So, the nth guy, right. So, gives me the bit pattern bn and from xn, right. So, after flipping it becomes yn, flipping it with certain probability or xn prime flipping it with certain probability becomes yn, becomes bn, right. So, this ratio, right. So, what would this ratio be, right. So, now this ratio, why do I need this ratio? I need this ratio because that is the only guy that seems to be different between 1 and 2, and somehow I want to get a handle on that ratio, and then I will use it to say something about the ratio of the mechanisms generating the same bit pattern itself. That is where we are headed, right. So, so let's try to focus on this ratio. So, now what can this ratio be, right. So, there is a truth xn, let us say, and if bn is a bit, right. So, the nth bit, let us say the bn bit is same as the xn value, Okay. So, then what am I asking? Well, what is the probability that yn equals Pn divided by yn prime equals Pn? So, if Bn equals Xn, that is the nth guy's truth is not flipped, right. So, with what probability did yn not flip is what is the numerator of this? Well, I know what that probability, right. So, that is just e to the epsilon by 1 plus e to the epsilon divided by, now what would the denominator be? Well, it is the probability that yn prime equals Pn, but yn and so but xn and xn prime are differing, right. So, if xn is Bn, then xn prime cannot be Bn, which means that if yn prime has to be Bn, then xn prime should have gotten flipped because xn prime is not Bn, because we have assumed here Bn is xn, which means that in that case what should have happened is the following. So, this guy will just be the flipping probability, which is 1 by 1 plus e to the epsilon. So, this whole thing is just then e to the epsilon. This happens if Bn equals Xn, right. So, Bn can be either Xn or not Xn. If Bn is Xn, then this is the non-flipping probability divided by the flipping probability. The other case is when Bn is not equals Xn, that is Bn equals 1 minus Xn, right. So, it is the opposite of Xn, in which case yn will be the flipping probability and yn prime will be the non-flipping probability, which means that what I will get in that case would be the following, would just be 1 by 1 plus e to the epsilon divided by e to the epsilon by 1 plus e to the epsilon, which is just e to the minus epsilon, 1 by e to the epsilon, which would just be e to the minus epsilon. So, irrespective of whether Bn is Xn or Bn is not Xn, you either get this ratio as bounded by as e to the epsilon or e to the minus epsilon, which means that in both cases we have an interesting situation where we can say probability of yn equals Pn divided by probability of yn prime equals Pn is less than or equal to e to the epsilon, because e to the minus epsilon will be less than or equal to e to the epsilon in both the cases. In other words, we have the following, which is probability of yn equals Pn is at most e to the epsilon times probability of yn prime equals Pn. Now, why is this useful? So, let me call this 3. Now, why is this useful? It is useful because now I can bound, I will use 1, 2 and 3 together, right. So, this is same as this. So, now if I divide probability of RR of x generating a bit pattern B divided by the probability that RR x prime generating the same bit pattern P, that is if I want probability of RR of x equals B divided by probability of RR of x prime equals B. Okay. So, now this is simply what we have here, right. So, the ratio is simply the ratio, which is probability of yn equals Pn divided by the probability of yn prime equals Pn, because the remaining are exactly the same, and we by 3 this is this is from 1 and 2 and this is at most e to the epsilon and this is from 3, and which means essentially what we are then saying is something very interesting, that the ratio of the probabilities RR of x equals B is bounded by e to the epsilon, or in other words this is e to the epsilon into probability of RR of x prime equals B. So, what does this tell us, right? So, this is what we have proved, right? So, let's stare at this for a second and try to understand what does this equation actually mean. It means something very fundamentally interesting, right? So, this is what I observe, right? So, I observe B and I want to know whether it comes from x or x prime via this randomized mechanism. Now, what this is saying is that the chance that it comes from X, that is the data set X generated this bit pattern B after going through this randomized mechanism, randomized response mechanism, is not too far away from the chance that the data set X prime generated the same bit pattern B, which means that the chance that just by looking at B, I am unable to say whether it came from X, did X generate this B or did X prime generate this B. The chance that X generates this B is at most e to the epsilon times the chance that X prime generates this B. And for small enough epsilon, so these two chances are close to each other, which means that even if I know that n minus 1 guys are same for X and X prime, in other words, now think of it from an adversary's point of view, right? So, somehow I have gotten hold of information of x1, x2, x3, the true information of n minus 1 people out of n people, and you are the only person whose truth I do not know as an adversary, right? And now you have added your information to the data set. I do not know your information can be 1 or 0. If you add 1 and now the randomized response generates certain mechanism and I observe a bit pattern B, versus if you had 0 and the randomized mechanism generates another bit pattern, just by looking at this bit pattern, it's still hard for me to say whether you are 1 or 0, because I don't know whether X generated this or X prime generated this. If I know X generated this, right? So, if I know which data set generated this, which means that I will be able to know what your truth is. What I am saying is that you now, as an individual who wants to put your data into the system, is much more willing to do so, because even if the adversary has access to everybody else except you, still you providing your information is going to reveal something to the adversary from which the adversary will not be able to figure out your particular information. And this is true for everybody, and so everybody is happy to give their information, right? So, essentially we are saying, even if a powerful adversary who knows everything except your information is still going to suffer, it's still going to be confused whether your information is 0 or 1. And how much confused will it be? Well, that depends on what this epsilon is, right? So, remember, this is not only one way, right? So, I could have done the same argument and then we could have gotten probability of randomized response of X prime being B is at most e to the epsilon times probability of RR of X equal to B. It's a symmetric argument that you can do, right? So, in both sides this is going to be true, right? So, in other words, what I am essentially saying is that this also implies we have RR of X prime equal to B divided by e to the epsilon, or in other words into e to the minus epsilon, is at most probability of RR of X equals B is less than or equal to e to the epsilon times probability of RR of X prime equals B. So, the first inequality comes from completely flipping X and X prime and doing the same argument. The second inequality is what we proved now. So, basically the idea is that it's bounded on both sides, and so for instance, if epsilon is 0 now, then this bound becomes tight on both sides, and these two probabilities will be the same, because if epsilon is 0, the randomized response is completely giving noise, right? So, random, half probability it's flipping things and giving me, I don't have any utility at all. Only if epsilon is non-zero, then I have some notion of utility, but how much how much can I figure out whether it is X or X prime will tell me how private this whole mechanism is, and that I can control with this simple number epsilon, right? So, which means that should I reveal the truth with 60%, should I reveal the truth with 70%, is something that epsilon is controlling, right? So, because by choosing epsilon suitably, I will reveal the truth with whatever percentage, right? So, that is e to the epsilon by 1 plus e to the epsilon. I can control how much percentage I will reveal the truth. Now, the more the truth that I reveal, the less the private it's going to be, because these probabilities are going to get separated, well separated out, which means that the more likely I would be able to guess whether it's x or x prime. The closer these two are, the less likely my distinguishing capability between x and x prime to have generated the observed bit pattern B. So that's the control that epsilon gives me. That's fine, right? So, but now we want to also ask the question, how good is this whole business of revealing the truth with slightly more than 50% chance, right? So, how much should I reveal, right? So, in other words, we want to ask a question not just about privacy. This is the privacy proof that we did, right? So, it is private up to a factor of e to the epsilon. That's the privacy guarantee that we have, right? So, now you can make e to the epsilon as small a number as you want to get as much privacy as you want. Now, we also want to ask the question, how useful is this information, right? So, as a function of epsilon. In other words, can we talk about utility of the mechanism? As a function of epsilon, how useful is this mechanism, right? So now I want you to pause and think, how would epsilon affect the utility, right? So not exactly in terms of numbers, but I want you to think about relative quantities, right? So if epsilon becomes smaller, do you expect the utility to become smaller or greater? Now, what is utility here? Let me tell you that before you can pause and think. By utility, I mean that you really want to average the truth, but what you can do is only do something with what is revealed to you, right? So now the information, the estimator for the truth, which is the average of xi's, how much can you get close to that by observing this bit pattern which comes out of the randomized response. That's what utility means, right? So and that's what we want to ask next, right? So if you want to pause and think for a second to understand how does utility change as a function of epsilon, please feel free to do so. What we will do next is start thinking about utility of the randomized response mechanism. Okay, so how good is this mechanism? So what do we want? We want 1 over n sum over I equals 1 to n xi. This is the average that I want to estimate, right? So if you remember the survey example, so I want to know what is the fraction of people who actually voted in my locality, right? So this is the truth, this is the true value. But what is happening is, there is this xi which is 0 or 1, but my randomized response randomizes this, right? So there is a randomization that happens. I don't get to observe xi, I only get to observe yi, right? So now and the question is, how good is this yi itself in telling me about xi, right? So yi can be thought of as an estimator for xi, right? So it's kind of it's estimating xi, but it's not exactly xi itself, because there is a random thing that has happened, right? So random process that has flipped xi with certain probability. So now what is the expected value of yi? On an average, what should I expect yi to be? That's a question that I can ask, right? So because yi is a random variable, xi is not random. Xi is a fixed truth whether I voted or not, whether the ith person voted or not, whereas yi is a messed up version of xi, so it's a random quantity, and I ask what is the expected value of yi, right? So, well, what yi is exactly, it can take either xi or it can take value 1 minus xi. These are the only two values it can take. It will take xi's value with probability e to the epsilon by 1 plus e to the epsilon. That is the chance with which I reveal the truth, and the chance with which I reveal the opposite of the truth is, which is 1 minus xi, is 1 by 1 plus e to the epsilon. This is the fraction with which, this is the chance with which I will flip. So on an average, the expected value is going to be the sum of these two, which if you just work it out, is e to the epsilon xi plus 1 minus xi by 1 plus e to the epsilon, which is which can be thought of as xi into e to the epsilon minus 1 by e to the epsilon plus 1 plus 1 by 1 plus e to the epsilon. This is the expected value, right. So, now what is happening is the expected value of yi is not xi in this case, right. So, it happens to be some scaled and translated version of xi. In other words, even if the ith person did this randomized response and gave me not just a single yi, but then kept giving me, kept tossing this coin and again, and then flipping or not flipping accordingly to what the coin falls heads or tails, and then giving me not just a single piece of information, but let us say he gives me infinite pieces of information, which means I can average this infinite pieces of information, I can get an expected value of yi, and that is also not xi. That is what this is revealing me, right. So, it is saying that on an average yi is not still xi, it is some, some scaled and translated version of xi. But me as a surveyor, I know the mechanism that we have agreed upon, right. So, all of you are flipping with some probability epsilon, I know that, and so what I can do is, there is a true xi and then it became yi, and now what I am going to make yi is, I am going to make yi, in other words, I am going to, sometimes it is called as unbiasing. If you are aware of the statistical terminology, yi is a biased estimator for xi, because the expected value of yi is not xi. So, we kind of, in this case, because we know that the distribution that generates yi from xi, we can unbias it or debias it. So, the way we will do that is, we will set zi equals yi minus 1 by 1 plus e to the epsilon into 1 plus, or rather into e to the epsilon plus 1 by e to the epsilon minus 1. Okay. So, what is this doing? It is basically, what I am doing is that I have this extra term which got added to the expected value and extra scaling factor which got added to the expected value. First, I am removing that extra term by subtracting it out from yi, and then I am cancelling the scaling factor by multiplying it with by its reciprocal, right. So, which means the advantage that I have now is, now if I compute the expected value of zi, now this would just be xi, right. So, take this as an exercise. I mean, it's very easy to show, it just needs some simple properties of expectation, but what I am essentially saying is the following, right. So, if I had to, so why are we doing all this? We are doing all this because we want a good estimator for the average of xi's, right. So, that's what we really want. We want a good estimator for the average of xi's, but we have only yi's, and yi has this problem that, it is not a very good estimator for xi because of the way in which we are tossing coins and so on. So, what we are essentially doing is, we are unbiasing or debiasing yi to get zi's which are better estimators for xi's, and now what we will do is, we will do the following. So, basically you had the truth is x1 to xn, and then what was revealed to you was y1 to yn, and because you care about the average, what you do is, you convert y1 to z1 to zn, and the way you convert is using this transformation that I just mentioned earlier, and now your guess for, you want to find out 1 over n sum over I xi, you want that, right. So, and now you want a guess for x bar, your guess for x bar is z bar, which is 1 over n sum over I equals 1 to n z. You are essentially guessing the average of the truth to be the average of the zi's. Remember, zi's are all random quantities. Why is zi random? Because yi's were random. Why is yi random? Because xi was not revealed truthfully, it was revealed truthfully only with certain probabilities. So, yi's are random. and now I am tinkering with yi to get zi's, right. So I am separating out something from yi, dividing it by something. Those are all not random quantities, those are fixed quantities that depended on my knowledge of epsilon, and nevertheless you take a random quantity, add something or subtract something, multiply something, it will still remain random. So zi's are all random, and now the average of zi's will also be a random quantity, right. So now the another exercise, again a simple exercise, the expected value of z bar, you can try to calculate what is the expected value of z bar. The answer is x bar, and it would be a good exercise to find out why this is the case. So basically what we are saying is that we want x bar, and now we can calculate z bar. Z bar is a random quantity, so it's not x bar. It changes if you repeat the experiment again, it's going to give you a different value. But on an average, if you repeated the experiment multiple times, which you cannot do in practice, but if you had the hypothetical power to repeat the experiment multiple times in practice, the average value of z bar over these multiple infinite experiments is in fact x bar. That's at least you are kind of reconciling with the fact that I cannot do the experiment multiple times, but at least if I had the power to do so, I would recover x bar truthfully, right. So but I can't do that, but at least in the infinite experimental case, I am able to recover x bar, and so z bar is a reasonable estimator for x bar, right. So that's what this statement is essentially saying. Statisticians would say that z bar is an unbiased estimator for x bar. Anyway, so what we have is z bar, that is the only thing that we have in our hand. Now the utility then that we really care about, let me define the formal utility definition, is the following, right. So I want the following quantity, which I have been saying multiple times, x bar, which is just the average of xi's, but what I can really calculate is from data after the randomized response mechanism goes through, I am only able to calculate 1 over n sum over I equals 1 to n zi, the z bar. And now I ask the question, hey, what is the difference between these two guys, right. So now the difference is not a deterministic quantity because this is random, zi is a random, so z bars are random, so its deviation from the truth is also random, but we can use tools of probability, and I won't do that in this course. We can use tools of probability to argue that with high probability, these two things are not going to be too far away from each other, right. So we can say that the chance that this is far away is, with high probability, this difference is at most something like 1 by epsilon square root of n. Well, it's order of this, but yeah. So this is something that can be proved using standard concentration bounds. Of course, if you are interested, you can use something like a Chernoff bound to prove this, but I won't do that. But what I want to say is that this is the utility of the mechanism itself. What is this telling us, right? So now let's take a step back and try to understand this whole thing that we have done so far. We have put down a mechanism in place where every person is not going to reveal the truth per se, but is going to flip the truth with certain probability, which is less than 50% depending on epsilon, and then going to give me the answer. Now we know that if you do that, then it has a nice privacy guarantee that an adversary who has access to everything except one person's information still won't be able to tell whether that person's information is 0 or 1. In other words, whether the data set that generated the bit pattern is x or x prime, with certain, the ratio of the probabilities of these two data sets generating the same bit pattern is bounded by e to the epsilon. So epsilon kind of controls the amount of confidence with which I am confusing the adversary between x and x prime. That's the privacy part. Now that epsilon should also play a role in the utility, and that's what we are saying here, right. So now we are saying, well, because everybody is giving me not exact information but only this revealing a random flipped version of it, I can use the random flipped version, I can receive this and then debias it and get an estimator for the exact truth, which is the average of the xi's that I really care about, and I am saying the deviation between the truth, which is x bar, and what I will be able to a number that between 0 and 1 that I will be able to get from the data, y1 to yn, convert it to z1 to zn and average zi's, this deviation is not too much, right. So, what do I mean by not too much? Well, the deviation also depends on epsilon. How does it depend on epsilon? If epsilon is smaller, the smaller the epsilon is, the deviation is larger, right. So, because epsilon here is in the denominator, that is the interesting fact, right. So, the smaller the epsilon, the deviation is larger. In other words, what I will be able to get as an estimate for my truth can potentially deviate away from the truth. How much will it deviate? Well, that depends on what my epsilon is. If I make my epsilon smaller and smaller, then the average of zi's is not going to be a very good indicator for the average of xi's, right. So, their difference is going to potentially could be larger. The chance that they are differing by large is actually high. But if epsilon is large, then this chance becomes smaller. But the opposite happens with respect to privacy. If epsilon is large, here if epsilon being large is a good thing, because zi's and xi's are averages are closer, whereas if epsilon is large, then I will be able to distinguish between x and x prime as an adversary with more confidence. So, in other words, epsilon is a single parameter that kind of controls the privacy utility trade-off, right. So, let me put that down because that's an interesting thing to note down. Epsilon controls privacy utility trade-off. Okay. The other thing that matters for the utility is the number of people I am surveying in this case. That is also revealed in this quantity that I put down here, which is 1 over epsilon square root of n. This is also telling me that the more, so for a fixed epsilon, the moment I fix an epsilon, then I have a certain amount of privacy guaranteed. Now, the question is, how much utility do I guarantee, right? So, now I am saying the utility for a fixed epsilon becomes better and better as I survey more and more people. Why is that? Because as n becomes larger and larger, even if epsilon is fixed, if n becomes larger and larger, then this is telling me that the deviation between z bar and x bar becomes smaller and smaller. Remember, n did not play a role in the privacy aspect of it, and that is an important point to note, right. So, why? Because now this is then telling me the following, right. So, if I want to achieve a certain amount of privacy, which means that for the moment privacy is more important to me than utility, then I would say that, hey, I need certain amount of privacy, right. So, which means that I can bound the ratio e to the epsilon by certain amount, and for that I can work out what the epsilon should be, and that will guarantee me privacy. Now, if I also want a certain amount of utility, now that epsilon is already been fixed, the only way then I can achieve a certain amount of utility then is to go back to this particular quantity and say that how many people should I survey, right. So, if I want epsilon to be certain value, let us say 0.5 or something like that, so then I am going to get e to the 0.5 as my privacy guarantee. Now, if I want a utility guarantee to be, these two ratios should not be more than 0.001 or something like that, then this is, I can rework things, right. So, I will set epsilon to be 0.5, and now that means that I want 1 by 0.5 into square root of n to be at most 0.001, which is the utility amount that I want, which means that now I will rework and say that, well, the number of people I should survey then should be a function of my amount of privacy I want and the amount of utility I want, and these three things kind of coexist with each other, right. So, if I fix a privacy and if I fix the number of people I am surveying, then the utility is also fixed. I cannot do much with the utility. On the other hand, if I fix a privacy and an utility, then to get such a privacy and utility guarantee, then you would have to survey at least these many people, right? So, and that's what this n would help us, right? So, and the big advantage is that the n does not appear in my privacy guarantee, right? So, if I fix an epsilon, privacy is fixed. If I fix a utility value, for the fixed epsilon, then an n will achieve such a utility value. So, yes, so essentially what we are saying is that this epsilon controls the privacy utility trade-off. The more the number of people you are surveying, the better it is for the utility for a fixed amount of privacy. So, this is the randomized response technique, where everybody flips or randomizes their data and then gives it to the curator or a surveyor, and then the surveyor does something with the data and computes an average, and the surveyor is interested in the average. Now, what we will see next is a slightly different model, which will get closer and closer to more our machine learning models, and in this model we have what is called as a trusted curator. It is a slightly different model from the randomized response models that we have seen earlier, and this is called as a trusted curator model, and this is what we will see next. So, in the trusted curator model, the only difference between what we saw in the survey example and the trusted curator model is the following. The curator is the surveyor there. The analog of the curator in the survey example is the surveyor. The problem there was the surveyor was not trusted. I was not trusting you, who is the surveyor, and so I flipped my data and gave you a flipped version of the data. I do want you to get a sense of what the global average is, and so I will not give you random information. I will give you some useful information, and how useful it is depends on epsilon and so on and so forth. That is what we saw earlier. But the main point there is that the curator is not trusted. Now, what you are going to say is the curator is a trusted curator, right? So, that is, I do not mind giving you my truthful data. You are a trusted curator. But then where is the privacy problem then, right? So, if I believe you, then I can give you my private information. So, the privacy problem in the trusted curator model happens because the curator is going to collect all the information, is trusted, is going to compute, let us say, the average or some function of the information that the curator collects from everybody, and releases this function to the world. Right. So, in the previous case, it is as if I believed the surveyor, I gave the information to the surveyor, and now the surveyor is collecting all the information, computes the average. Now, that will be a truthful average, right? And now the surveyor has to release this information to the world for public knowledge. Maybe the surveyor will put it out on a website saying that the average number of people in my locality who voted was certain number, 0.85 or something like that. Now, the world is not reliable, right? So, there may be people or adversaries in the world who might have knowledge about everything, everybody except one person, except you, and so you still have to worry about giving your data or not. Now, if the surveyor who is trusted or the curator who is trusted is fine, is not going to tamper with your data, or it's not a privacy concern as long as giving the data to the curator is concerned. But because the curator is releasing the average to the outside world, it might still be a privacy concern. Now what one way to solve this problem is, anyway it's finally going to the world, the average is going to the world. So, I might as well do the same thing as randomized response. I might not believe the surveyor or the curator itself and then give the curator himself the random version of my data. Let the curator do what he did in randomized response, and that is anyway going to be private and has certain amount of utility. The question that we are going to ask in this section is that, can we do better if we trust the curator, right? So, just to say this, right, so you have data and curator, and then it goes to the world. Okay. So, in the previous version, this part, both part are problematic, right? So they might be adversarial. The curator, you don't want even the curator to know your data. But in the second case that we are seeing, we are saying again we have a data, a curator, and the curator releases some function to the world. Now we are saying yes, the world might be problematic. By looking at the function, the world should not be able to figure out what my data is, but I don't bother if the curator figures out what my data is. I am happy giving the curator my data, I just don't want the world to know my data. That's the difference, right? Now, of course, if we are more pessimistic, we can believe that the curator also is problematic and whatever we did earlier will also work. But the question is, if this red dot becomes this green dot here, can we do better? That's the question we are asking. And the answer to this is yes, you can do better, and this will lead us to a very foundational and fundamental aspect of privacy, which we are going to see at some length in this course. It's what is called as differential privacy. So, which was introduced by Cynthia Dwork in her seminal paper back in 2010, I guess. So what we will do is we will look at the definition of differential privacy and some versions of differential privacy, and later on we will try to connect it to machine learning algorithms as well. So what we will start seeing next is the notion of differential privacy. Thank you.